It's my pleasure to introduce Saptashi Chakraborty, sorry. He did his PhD in statistics at the University of California, Berkeley, and joined us here at the University of Michigan as an assistant professor just in the fall. And he does a very interesting variety of work about analyzing low-dimensional probability spaces and for deep learning and other kinds of problems. So today we're very interested in hearing from Professor Chakraborty. So go ahead.
Thank you, Laura, for the wonderful introduction. So the talk is organized as follows. So today we're going to talk about the theoretical properties of diffusion models. And so just to be on the same page, I'll briefly introduce diffusion models, even though there are many experts in the room. Then we'll cover something called the intrinsic data dimension and try to characterize that for a probability distribution and see how that intrinsic data dimension plays an important role in the generalization bounds for such score matching diffusion models. And that will be followed by some inference, and we'll see that under some settings, this upper bound matches the minimax lower bound, making diffusion models minimax optimal. And if time permits, I'll also cover a proof sketch. And yeah, so this is joint work with Peter Bartlett and Quentin Bertrand. Both of them are at DeepMind. So just to give you a brief history of generative AI, well, it's all that people are talking about currently, and it has been so it has been a topic for recent research in for the past few years, and it mostly started from variational autoencoders back in 2013, 2014, followed by GANs, and now there are much more developed models. For example, diffusion models, their variants, flow matching, their variants, and so on. And this is also generated by a generative AI model, namely Claude. And yeah, so the setup is quite classical. So you have n independent and identically distributed data points, x1 through xn, coming from some distribution mu. And of course, we want to learn this mu from these n IID samples. And this mu is supported on this d-dimensional real space where D can be quite large. So for example, for ImageNet, you have 128 by 128 images, and your capital D is about 49,000. So D can be quite large, and we want to get a good model for this mu. So we want to get a good estimate for this data distribution. And the way diffusion model does this is as follows. So at time t equals 0, you start off from mu, you gradually add noise to it. So that's characterized by this forward diffusion process, or the OU process. You can think of this as the continuous time version of this adding noise at every step. So at time t, you're at some distribution pt, which is quite close to the normal distribution in this capital D dimensional space. And for this forward process, there exists a backward process. It's not necessarily unique, but we can characterize that through this backward diffusion model, which is given by this formula. So here, WT tilde is another Brownian motion. And so this YT is X capital T minus small t. So the main idea is that you start off from P capital T, and eventually at time t equals 0, you reach mu. So this grad log pt minus small t is known as the score function. And the whole problem of diffusion models is to learn this score function. So, but of course, we can't really start from mu. We have an estimate for mu. If we had mu, the life would be easy. But of course, we don't. So we have this mu hat, which is the empirical distribution based on n data samples. And at time t, I'll denote the distribution by pt hat, And again, you have this reverse process. So you have this different spikes. So here the data points are denoted in red, and eventually you reach this capital PT hat, which is hopefully quite close to the normal distribution. Now, we don't have access to the score function, but we try to estimate this. So we'll denote that with S. And the score matching objective is given by this formula. So you just find out the expected L2 difference between this estimated score and the true score, and you do this for this continuum of time from 0 to capital T, and you minimize this inside a function class script S, which is realized by neural networks. So in this talk, I'll talk about feed-forward neural networks, but by ReLU activation functions, but you can also use different other kinds of function classes. So people generally use UNets or attention-based models to characterize this script S. So you don't start off, so in the backward process, what people typically do is that you start off from the Gaussian distribution. So ideally, you should start from PT hat, but that's difficult to sample from. So we start off from this Gaussian distribution, and eventually we don't stop at T equals capital T. So we don't stop exactly at 0, we early stop. So at capital T minus delta, we stop this process because near 0, there's a variance inflation that happens in practice as well. And from a theoretical viewpoint, it also makes sense because if mu is lying on some manifold or some subspace, then there are some singularities that will blow up the variance. So we start off, so ideally we want to learn a continuous, or we want to do a continuous time reverse SDE, but also we don't have the luxury to do it. So what we do is that we discretize. So this is the reverse time scale. So you start off at T0 equals 0, T1 all the way up till T capital N, which is capital T minus delta. And throughout these time intervals, you keep these coefficients fixed. So you fix the score function, and so you just you just do the forward Euler process in this backward diffusion model. So you start off at some Gaussian distribution, and eventually what we want to argue is that we want to be very close to this mu. And our goal is to understand the difference between this mu and the estimate in terms of the Wasserstein P metric. So where P can be quite general, so 1 to whatever. So P is larger than 1. Well, larger than or equal to 1. And it can be easily seen that the reverse diffusion model that we have, so the reverse process, is exactly solved by an exponential integrator scheme. So you can exactly implement this through a closed form expression for each of these time points, T1 through Tn. So that involves simulating some Gaussian distributions, and you have a closed form expression of y t plus 1 in terms of yt. And yeah, so that's how people do in practice. And what we want to do is that instead of minimizing this objective, this integral, we discretize again. So at these different time points, we estimate this expectation through the corresponding, so we are just taking step function approximation of the corresponding integral, and we want to minimize this objective to get our SN hats. Here, HIs are the length of those intervals, and here script S is a class of functions from RG to R. So we talk about two different kind of estimators. One is the true one. So what we can show is that this objective by Gaussian integral by parts is exactly the same as minimizing this objective. So we have an expectation over both this Z and X's. So we minimize this objective, and with respect to S being in this script S, But of course, in practice, you do another step. You don't really minimize this expectation, but you take a Monte Carlo approximation of this expectation. So at each of these time points, we generate mi many samples, and mi many samples are generated from the distribution of xt, and you just take the average instead of taking the expectation, and that we called SNMC to denote Monte Carlos. But this is actually the estimator that people use in practice, but of course you do various modifications on top of this as well. But yeah, so in this talk, we'll analyze these two estimators, 1 and 2, and try to find out what bells and whistles we can optimize to get a good error bound for estimating the distribution when we use SN hat and SN hat MC. So our goal is to understand this, the performance of these two estimators. And at the same time, we want to understand how to select this core function class, how to select this optimal, how to get a value of this capital T for this forward process, the early stopping time for the reverse process, and the discretization scheme, as well as the number of Monte Carlo samples you need to generate at every step.
Is the
Yes.
beta T sequence also something you want to?
So we fix beta T, but there are some assumptions on beta T that it should be upper bounded and lower bounded. I think in practice, people just use beta T equals 1.
Oh.
But yeah. Early stopping is that you don't run the process until capital T. So capital T should be here. We just stop a little, like little before capital T. So at time capital T minus delta. Yeah. And of course, like, so if we have many samples, then we can choose delta to be very small, but we'll show that we can choose delta adaptively in terms of the number of samples. Yeah. Any other questions? All right, moving on. So we want to get, we want to get sufficient conditions on all these things. At the same time, we want to get an optimum rate for this Wasserstein distance between the observed and the estimated. Now, we want to understand how these diffusion models generalize so well. So one idea comes from the so-called manifold hypothesis, is that it says that real data often lies very close, well, maybe not exactly, but very close to a low-dimensional structure within this high-dimensional data space. And diffusion models, or in general deep learners, they're extremely good at capturing this low-dimensional structure. So this was a study done by Pope and collaborators. They used an estimator, very classical one by Levin and Bickel, where they estimated the intrinsic data dimension through some spatial Poisson process estimator. But what they found out was that for different image data sets, this intrinsic data dimension, or the estimate of it, is quite smaller compared to the extrinsic data dimension. So for example, considering MNIST images, the images are 28 by 28. So the extrinsic dimension is 784, but the intrinsic dimension is quite small, so maybe close to 10 or something. And for different image data sets, they can vary. So for example, for ImageNet, they calculate this to be around 40 or 45 or something. But this is the main idea, is that your images, they lie close to a manifold, and we want to understand whether this low dimensional structure plays an important role in finding out the generalization bounds for diffusion models. And in classical statistics, or in classical estimators, what we observe is that the error bounds, they often scale like this. So they often scale quite adversarially with capital D, which is the dimension or the extrinsic dimension of the data. And we want to understand whether instead of this capital D, we can get a small d, which is the intrinsic data dimension. So instead of getting 784 for MNIST here, which is prohibitively slow, we want to get maybe 10 or something. So to test this, we want to see whether this holds water in practice. So what we did was we generated two sets of image data distributions. So one that had a intrinsic dimension of 10, another intrinsic dimension of 100. So both of them, they have the same extrinsic data dimension, 128 by 128, but the intrinsic dimensions are different. And how we do this is as follows. So we have this pre-trained big GAN model, and we sever some of the initial connections in the first layer. So for d equals 10, we have this 10 connections, d equals 100, we have 100 connections, and we generate two data sets. So the way I think about it is that d equals 10 has a lot less details compared to d equals 100, even though their extrinsic dimensions are exactly the same. And we ran some experiments on finding out the generalization properties on such varying intrinsic dimensions, and they are as follows. So we varied the number of training samples, so increasing the number of training samples, and we plotted the FID scores for both these two data sets. And what we observed that for different classes, this intrinsic dimension plays a big role in the sense that if you have a higher intrinsic dimension, then the generalization is much slower compared to if you have a lower intrinsic dimension. So your FID scores, they decay much faster for d equals 10 versus d equals 100. And this is observed for different classes inside the ImageNet data. So this theory of manifold hypothesis, it holds water in practice in the sense that we get the behavior that we expect, that lower intrinsic dimension is easier to generalize, but how to characterize that theoretically? So the question we ask is as follows. So how does this manifold hypothesis affect our score matching diffusion models? How to select the optimal score network class? And how do we actually characterize this intrinsic data dimension? So to characterize this intrinsic data dimension, a good starting point is the so-called Minkowski dimension, so which is nothing but counting the number of boxes or counting the number of epsilon boxes you need to cover a set script M. So you just take the log covering number, divide with log 1 over epsilon, and take lim sup as epsilon goes to 0. And for a probability distribution mu, the Minkowski dimension of mu is simply defined as the Minkowski dimension of the support. So essentially you cover, you find out the number of boxes you need to cover your entire support. But this is really suboptimal, although people have used this Minkowski dimension to characterize the generalization properties of different deep learning methods. For example, GANs and even in simple linear regression, not linear, but simple additive regression settings, people have used this Minkowski dimension to characterize the intrinsic data dimension. But obviously, this Minkowski dimension has a very critical drawback in the sense that if your data doesn't lie exactly on the manifold or exactly on a low-dimensional space, but is scattered around a little away from this manifold, maybe not too much. So if your data distribution is highly concentrated on some of these subspaces or manifolds, but is thinly spread out across the entire data space, then this Minkowski dimension is not a very good characterization of the intrinsic data dimension. So what we do, we define something called the PQ Wasserstein dimension, but for that we need this epsilon tau covering number. So this epsilon tau covering number of a probability measure mu is simply the smallest covering number to cover a set that gives probability at least 1 minus tau. So you find out the cover of a set, you find out the number of epsilon boxes or epsilon balls you need to cover a probability of at least 1 minus tau. So for tau, yeah, you don't really care about a little region, but you only care about where the mass or where the chunk of the mass lies for this probability distribution. And of course, this tau will vary tau based on epsilon. So we define this PQ Wasserstein dimension. It's defined in a very weird way. But the main idea is that we want to understand the behavior of this log covering number, where epsilon varies like this. So this exponent is required in two settings. So one is that, so we will only assume a qth moment. We won't assume that the data is supported on a compact set. So a q moment condition, it brings, it harms a little bit. So that's one. Another one is that we need to cover, we only need to cover most of the support. We don't need to cover all the support, and this epsilon essentially works. So yeah. And this is quite inspired from this P Wasserstein dimension, which was first proposed by Witt and Bach, where they characterized the Wasserstein dimension in this way. And what we can show is that if you have a compactly supported data distribution, then the Wasserstein P distance between the observed and the empirical distribution, it scales, it's controlled by this P Wasserstein dimension. Any questions? Yes. Right. So the P, it comes from, we are trying to characterize the P Wasserstein distance, and Q comes from the fact that we only want to assume a moment or qth moment condition on the data distribution. So let me give you a theorem. So it says that, so this is the utility of the PQ Wasserstein dimension, is it says that if you have the data supported on the entire data space, but you have only a q finite moment condition, then the expected Wasserstein P distance between your true data distribution and the empirical distribution, it scales with n power p over d, where this d is a little larger than this Wasserstein dimension. So this little larger comes from the fact that we are using an infimum, so that limiting condition comes into play. But how you should think about is it's that d is very close to this d star, and the exponent of this n is controlled by this d star.
What is for like Gaussian Q? Every Q is okay.
Yes, for Gaussians, then you can take q to infinity. That's yeah, that's fine. And for Gaussians, we can show that yeah, I think we can show that you can take d star to be capital D itself. So for Gaussians, the dimensions they match, but we don't know if you have a low dimensional covariance structure or an eigenvalue decay, what happens. That's not known. Any other questions? All right. So the advantages of having this PQ Wasserstein dimension is that it works for distributions with unbounded support and also works for heavy tail distribution. Remember, we only need a finite qth moment condition. So it works for, so you don't need a sub-Gaussian tail or anything. And it works much beyond this subspaces and manifolds. Of course, subspaces and manifolds, they are a special case for this definition, in the sense that if your data is supported on a subspace or a manifold, then that exact dimension is realized by this d star. So d star is exactly that subspace dimension or the manifold dimension. And yeah, so it matches for those contexts. So through this intrinsic data dimension, we intend to characterize the generalization bounds for score matching diffusion models. And so let me start by putting the assumptions on the slide. So the assumptions are very simple. So we assume that x1 through xn, they're IID, and the qth moment is finite for some q larger than 2. Actually, q has to be larger than p as well, but q has to be at least larger than 2 because you're taking a L2 difference to match the score function. So that has to be finite. And we also assume that this beta t is upper bounded and lower bounded for some beta which is continuously differentiable. So in practice, I think people just take the OU process for which beta t is 1. So this assumption is also satisfied. So we need this assumption too to make sure that the forward process is stable enough. So it prevents some abrupt changes since this is continuously differentiable. And this assumption is also a sufficient condition to make sure that the reverse process exists and it admits the corresponding reverse stochastic differential equation. And this also helps us ensure that as the terminal time capital T goes to infinity, the forward process converges to the Gaussian distribution on capital D dimensions. So that's also an advantage of having such an assumption. Now, for the discretization scheme, we'll take a very standard discretization scheme that people used, at least in the theoretical study of diffusion models. So what we do is that we'll start off, we'll take this to be delta because we're stopping delta time before capital T. And so what we'll do is that we'll multiply this with kappa. So minimum of kappa and delta gives us the next step size, and the next one is also given by minimum of the previous step size with 1 multiplied with kappa, and so on. So this is sort of a geometric discretization scheme. So the differences here are much more, so the discretized time points, they're much closer together compared to as you move towards 0. So this is actually the starting point for the reverse process. So as you're very close to the Gaussian distribution, you don't need to discretize too much. But if you're moving towards 0, so meaning that you're closer to the data manifold now, then you need to be more careful, and your discretization has to be more closely spaced together. And this geometric type of a decay, it's quite standard in the theory of convergence of diffusion models, and people have used this scheme quite a lot, at least in theory, if not in practice. Any questions? All right. So with this exponential or geometric discretization scheme, so of course, let me briefly also introduce neural networks. These are functions of this form, but notationally, this RW, L, B, L, W, and B is a set of all neural networks realized by ReLU activation functions with depth scaling as L, number of weights W, and the size or the maximum weight as B. So only the two parameters that really matters are L and W, and as they control the VC dimension or the pseudo dimension of this network class. And what we want to understand is that what conditions or what sizes should we take the network class, this L, W, P, and other things, so that that gives us a sufficient condition to show convergence of the estimate of the true probability distribution. So one final thing before we move on to the theory is a little truncation. So we work with a truncated version of the reverse process. So after reaching the reverse, after reaching time t minus delta, we truncate the distribution at R. So each side is 2R, but of course we'll try to also choose R based on the number of data samples that we observe. And remember, we have these two estimators. So just wanted to briefly recap that. So our main result is as follows. So it says that if you choose capital T large enough, so it depends on everything. So depending on the number of data points, P, Q, Wasserstein dimension, full dimension, L2, second moment, etc. And if we choose R to be scaling with this, delta scaling with this, and kappa scaling with this, we can show that the expected Wasserstein P distance between the true distribution and the truncated distribution at R for our estimator 1 is scales with this. So n power minus 1 over the pqth Wasserstein dimension, followed by some polylog n terms. And we can also give bounds, a sufficient condition on the network size, meaning L should scale with log n, B scaling with some poly of n, and W also scaling with some polylog of n. So yeah, so from this analysis, this gives a sufficient condition for an upper bound on the expected Wasserstein P distance for estimator 1. And under the same knobs and bolts for T, R, delta, and kappa, we can show a similar bound for our estimator 2. So in that case, we need to select L, B, and W scaling quite similarly. But in this case, we can also give a lower bound, a sufficient condition for the number of Monte Carlo samples that we need to generate for every time step. So if we select the network architectures, all these T, delta, kappa MIs, then we can show that the score matching diffusion model, its Wasserstein P distance from the actual distribution, it scales with the Wasserstein dimension of mu. Any questions? Yeah. Yeah, good. Yes.
Yeah, and then it seems like you should also need lower bounds, right? But
Right.
like, it should be approximately this.
So we just give a sufficient condition on how large the network sizes should be. So L is the depth of this network. So L in our analysis is scales with log n. So it's a very wide network. So the number of layers, they scale with log n, but I think the maximum width, it scales with some poly of n. Yeah.
Has to be small, can't be too small also, so.
Right.
But it's still what you wrote, looked like an upper bound only, so.
Right. Yes. So yeah. So yes. So this should be asymptotic. Yeah. This should be asymptotically same. Yeah. But yeah. So this is so yeah. I guess I wrote this twiddle upper bound because it's enough to choose L, B, and W, and the size of this, it scales at most log n. That's sufficient to have. So yes, so it should be actually like asymptotically same, but yes. Yeah, so this gives a sufficient condition on B, W, and L, and R is the truncation in the reverse process. So after reaching this after reaching this Q hat T minus delta, we truncate at the rth step. So, or we truncate at size R. So meaning that if the data point or if the distributions give mass outside this region, we'll just set it to 0. So we get a peak at delta, which is the probability of whatever lies outside this R region, but inside we remain the same. And we increase R with the sample size as well. So if we have more and more samples, it's sufficient to choose R quite large. So we don't need to truncate at a smaller level compared to if we had more samples, you can truncate further away from 0.
What would happen in that bound in the next slide?
Yes.
If you just did the truncate mu also?
So we are not truncating mu, but the proof idea is that you truncate mu as well. So truncated mu and truncated distribution, they're close together, and mu truncated, they're also quite close together if R is large enough.
But the other one probably dominates. Truncated mu to the truncated this must be even faster.
Yes, the trunk.
That rate.
That I don't, we didn't explicitly calculate that. But it's somewhere in the proof, but we didn't explicitly look at it. Yeah.
And that must be like when practice, when one sees that things look good.
Right.
It must be the truncated versus truncated looks small.
Right.
Tails must not show up. Like
yes.
Wait.
Yeah. So yes. So that So the finite qth moment condition helps in that aspect, that the truncation is not that bad. Yeah.
Is that faster than 1 over D? truncated to truncated?
That I'll have to look into, but yeah, I don't know. Yeah, off the top of my head, yeah, I don't know.
On the next slide, the next area tape.
Yep.
For N, you have the sigma in the fourth. Now, remind me which, that sigma is not the activation function, obviously. What
No, yeah, so yes, I didn't introduce this sigma, but sigma is this. So, yeah, for the OU process, sigma is sigma squared T is 1 minus 2 bar minus 2T.
Oh, so it's unit.
Yeah. So it's bounded between 0 and 1, but it can be very close to 0 as well. And this H is their, yeah, they also depend on T as well. So it depends on the ratio of these two quantities. But having this sigma here, it will contribute to some polynomial in N again. So this entire thing remains a polynomial still.
And the constant out front is, we know that constant or not? Just give us guidance for how many samples.
Yes. So I think we have an explicit bound on the constant as well. So yeah. So combining all these terms is coming in a later slide. Yeah.
Yes. The division fee.
Yes. So the estimators, yeah, the error rates and the size of the networks, they all depend on the low dimensional D and capital D as well. Both.
We need first have an estimation of the low dimensional D.
Right.
We can construct. Okay.
Right. Yes, but yeah. Yeah, in principle, yes. Like if we have access to both this small d and capital D, then we should be able to learn nicely, but there are also constants lurking around which can also affect the performance. Yeah.
So regarding for the class of the network, the constraint for the layer perceptron is still not sure, right?
Sorry?
Considering the architectures for the.
Yes, so yes, I'm just talking about feed forward multilayer. Yeah.
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 That is mostly for
Right. Yeah, so yes, that's a very interesting question. I think, yeah, that's quite open. And so the thing that we use in this paper is ReLU networks or feed-forward neural networks. They have a good approximation, like they have good approximation properties, which we can hammer into in our analysis. But for convolutional networks, these approximation properties are not that well known, I would say. So for example, in some steps, we need to approximate a Lipschitz function. We know how to do that using a feed-forward neural network. But for convolutional networks or more generally UNets or something else, we don't really have a good bound for it. So yeah.
There's some ways using this insight can also infer in the solution through some approximation way, or.
I think to do for convolutions, we need to develop the theory for approximations through convolutional networks, which which might be which should be feasible, but yeah, should take some work. Yeah. Yeah.
Theorems can like approximate other
Right.
functions or something.
Yes. Then the theory should go through. Yes. Yeah.
I think that they're saying that in order to have the right-hand side sentence loss or whatever, we only requires the level of the layers for the network, right?
Right.
So we are constructing the network, so that means like having more layers doesn't harm, right?
Yes.
It's always better.
Yes, we're saying it's sufficient to have this, but yes, increasing might not harm as well.
Yeah.
Yeah. Yes, yeah, you can't. So what we show that in some cases this is optimal. So you can't go much below this.
They are showing that for this kind of multi-layer exceptions, the expressivity of these networks is like scale is like maybe square root of L. But here it's like if you have n samples, you need more than layers, which is like to me like the L only have like exponential expressivity in terms of its training samples.
Right. So so the proof is constructive, and what people generally do is that they have this network stacked one top of each other. That's why we have a very wide network, but we don't need a much deeper network in that case. Like it's constructive. So I would imagine if you have if you increase L, the expressivity power might also increase. But approximation theory is mostly studied for wide networks. Deep networks, it's not that well known or not well developed. Yeah.
What do you mean by stacking the networks on top of each other?
So essentially, whenever you're approximating, say you're approximating a function, so what you do is that you define these grids, and on each of these grids, you have a good enough function approximation, and you just stack the networks on top of each other. And if you're in a grid, then only that network spikes. Yeah.
Or like switching and stacking, I guess.
Yeah.
Between different.
Yeah. So we have these two bounds, and so let's go into some inference. So in simpler terms, this score matching diffusion models, it can achieve, if we disregard this polylog n terms, it's n power minus 1 over this p qth Wasserstein dimension under a finite qth moment condition. And this gives the fastest known rate for score matching diffusion models compared to the existing literature. So existing literature mostly looks into Wasserstein 1 or Wasserstein 2 distances, and there are some suboptimal constants which we can completely bypass in this analysis. And if your data is exactly supported on a manifold, then if P is between 1 and D over 2, then this D star is D. Like, so for all practical purposes, you can think of P as 1 or 2 or something, and D to be a little larger than P, so maybe D is 10. So this condition holds. And for those cases, this intrinsic data dimension is exactly D. So special cases include non-empty convex subsets of affine spaces with D dimensions, boundary of a set with D plus 1 dimensions, self-similar sets with dimension D, and of course, compact D-dimensional differentiable manifolds as well. So all of them, they become special cases if your data is exactly supported on these sets. Now, for the choice of the stopping times, so for the forward process, t needs to be larger than this. So if we ignore all these terms in p and q, so it scales with log n over the dimension. So if you also disregard the dimension, it's sufficient to choose t to be scaling with log n. And it's also sufficient to choose delta to be scaling with n power 2 over this constant. So it decays polynomially with n. So if you have more and more samples, then you can truncate closer and closer to capital T. And that's also characterized by this number of, delta scaling with polynomially with the number of samples. And also for the truncation, we can choose R to be scaling with n power something. So with n, we can choose R to be polynomially increasing with n as well. So if you have more and more samples, it's sufficient to scale, or it's sufficient to truncate at a further and further point. Now for the discretization scheme, we choose kappa to be scaling with this. So the interval length, they become shorter and shorter as well. So kappa scales with n power minus something. So if you increase the number of data points, your discretization points, they become closer and closer together. And the number of points you have in the discretization scheme, it's given by this. And that also scales with some polynomial of n that depends on p, q, this intrinsic dimension, and so on. So if you had a non-geometric discretization scheme, then this nice log 1 over delta won't appear. So if you don't have a discretization scheme that's geometrically scaling, but scaling, if you have the discretization scheme equally spaced, then this n, it scales with I think delta power minus 2 plus some t over kappa or something. So the advantage is that with this geometric discretization scheme, you do it with a much smaller number of discrete points compared to if you had a fixed length for the intervals. And also for the number of Monte Carlo samples, we have so what we can show is that the total number of Monte Carlo samples, if you choose everything nicely, it scales like this. So this is A plus capital D over this B plus something times the intrinsic data dimension. So this is something that we also observe in GANs as well, and other people's also, they also observe for GANs, that the number of Monte Carlo samples in terms of the exponent of n, it scales with capital D over small d. So if you have like a needle in a haystack problem, so you have a very, very low dimensional data distribution in a very high dimensional space, you need a much larger number of Monte Carlo samples compared to if you had otherwise. And this dependence is quite bad, but at the same time, this appears in many other recent works as well. So so I don't know if this dependence can be made better or not.
And in practice, are people, what numbers are they using, you know?
They take m to be more than n, that's for sure. Like the number of Monte Carlo samples, at least in GANs, they do it much larger than the number of actual samples that you observe.
Sum over m sub I. I mean, but m sub I is greater than n? Like,
No. Yeah, so m is sum over m sub i's, and
yes.
Yeah, I don't know if they like take it with this scale, but certainly I think people use the number of Monte Carlo samples larger than n. At least for GANs they do. I'm not sure about diffusions. Yeah.
Then like if D is 300 or something, it really is not n to the 300.
No, definitely not. That's not something people use in practice, right? Yes.
But you think the gap is by the theory can versus extra cost compared to the practice?
Right. So in this context, what the proof technique it does is that it derives a generalization bound for estimating this expectation. And that might not be the best thing to do because the generalization bounds, they also depend on the size of the networks, and which can grow quite large. And yeah, I think so in this paper and in related works as well, people really haven't tackled optimization error yet. Maybe the optimization landscape is better behaved. Maybe like the solutions, they converge to some nice solutions that have better generalization properties. Yeah. So we also have a matching lower bound. So forget about this light-tailed or heavy-tailed things. We are now inside this compactly supported space, 0, 1 to the capital D. And for this, we consider all distributions supported on script M, where script M, you can think of script M as a manifold, but it doesn't need to be a manifold. It only needs to have a lower Minkowski dimension, which is defined like this. So for the set of all distributions supported on a specific set, what we can show is that the minimax lower bound, it scales with the lower Minkowski dimension minus some delta. So this delta is an artifact of the lim-inf again. So if you have a bound on the exact covering number, this delta can be replaced. And For GANs, or yeah, not for GANs, for diffusions, what we can show is that if M, the data support, is regular enough with the dimension D, for example, if M is a manifold or a subspace, some nice regular sets, then both the lower Minkowski dimension and the PQ Wasserstein dimension, they are D. So both the upper and lower bound, they're roughly similar, roughly in the sense that there might be some delta minus in the lower bound, some plus delta in the upper bound, so that yeah, it roughly matches, but these deltas, they are an artifact of the definition of the infimum in both cases. I guess we can, yeah, we can skip the bulk of the proof sketch, but it's quite simple really. So we decompose this error into various parts: generalization, early stopping of the forward process, score approximation, discretization, early stopping of the backward process, and truncation. And we control all of these quite nicely. So you have all these knobs to tune, and ultimately you can get the bound that you want to observe. So yeah, in these two slides, yeah, you can get good bounds on all these errors, and of course the devil lies in the details. So in conclusion, in this work we have developed a generalization theory for diffusion models, and we can show that the error rates, they depend only in terms of the number of data samples, they only depend on the intrinsic data dimension rather than the extrinsic dimension. And we define this intrinsic dimension under very mild regularity conditions, in the sense that we also allow for heavy-tailed, or yeah, so we also allow for heavy tails in our analysis in terms of the qth moment. This theory also covers union of subspaces, manifold, and other regular distributions. And of course, the model size increases with the sample size. That's a sufficient condition for our model, for our generalization theory to hold. Of course, we don't know if that's necessary or not. And it's sufficient to choose our capital T scaling with log n, D scaling with 1 over some poly of n, R scaling with some poly of n, capital N, that's the number of discretization steps, scaling with polylog, and the gaps kappa, also scaling with 1 over poly of n. Is sufficient to choose these knobs. And in some cases, we can show that score matching diffusions, they are minimax optimal if the support is regular enough. Of course, there's a lot of gap in the current analysis, and there's a lot of open questions, especially in the optimization properties of diffusion models. Virtually, there's not much literature on that topic. And these are some of the papers that we mentioned. And yeah, thank you. Yes.
Oh.
That's a good question. Currently, there isn't, but I can imagine that if you take all distributions, set of all distributions such that mu is dominated by nu, so you have a distribution and you're considering all distributions that are dominated by that, then if you consider this class, then probably the lower bound will be in terms of some dimension of nu, which might include the PQth Wasserstein dimension. But yeah, we haven't really thought much about it. Yeah.
Something from HR beginning, how to create the intrinsic low-dimensional data,
Mhm.
having some job in the first latent embedding layer
Yeah.
began. I wonder, like, why do you choose that layer, and why isn't in the latent space of the for example, GAN generation? So for
Right.
that, we have like the latent or some like the distribution to be to control like the generation, right? So it seems like maybe more intuitive to just define my latent space is like the what kind of dimension.
Right.
right? So why do you want to create this kind of the low dimension intrinsic data from just the cut of layer?
Right. Yeah. So if we sever some of the initial connections, so that automatically reduces the latent space dimension to that d equals 10 or d equals 100. So that's yeah. So that's something that works, that automatically it reduces the latent space dimension. And since we already have a big GAN, which is very good at generating data, so we chose that model. Another one is I think in the literature also, Pope and collaborators, they also choose this way to generate the data. But yeah, it might be worthwhile exploring whether training a GAN with that corresponding latent space dimension, it helps in creating low dimensional images. Yeah.
So recently, see some like the generator working on the like the dynamic MRI image with the breathing. So
Right.
you see the latent space where the latent vector is 12. But we find like in the result after we do the PCA in the latent space, so the main like directions is only rank of 2.
Right.
So which means that it's definitely low rank, right? So we can be able to train this kind of data that can be able to achieve the low rank, maybe more exactly from the big N.
Right.
Yes.
Right. Yeah. Yeah. That might. Yeah, I don't know if that generation process, it should give similar, similar decay in the generalization bounds, but yeah, might be, worthwhile exploring. Yeah.
It's good one. It's good. I just want to ask, what is the point, in considering this process and distance? Because like I think most people consider KL that.
Right. Yes. So KL is good and nice, but when you have data that are singularly supported, for example, manifold or subspaces, KL is not well defined. So if you have singularities, then KL will be blowing up even if you have approximations. So yeah, so that's the problem. So if you have a data supported on, let's say, a line, let's say, and you have an approximation that's very close to this line, then KL will be infinity, but Wasserstein will make sense.
Maybe in that same spirit, what would be the, like, in practice, it doesn't look like it's this bad, but
Right.
the, that instead of optimizing over all the distance, like what do you sense might be, it feels like indirectly during the training, it's not optimizing over all distribution in some way.
Right.
What do you feel might be the formulation that might give what do you sense is the empirically observed rate, and what would be the reformulation that would somehow be able to reveal the actual observed performance versus this worst case that one is never really
Right.
optimizing?
Right, that's a good question. And yeah, in short, I don't really know, but maybe starting from a simplistic model, for example, let's say a mixture of Gaussians or something. Yeah. Maybe have a good enough latent space model might be a good starting point, but yeah, off the top of my head, I don't know.
As an empirically, yeah, so the training of the bigger distribution model is actually based on different data intrinsically. Because we find some data is very hard, but in others it's easier. So I think that kind of the conclusion from the theoretical side, I think is really pretty even though we don't know what kind of the manifold is easier.
What do you sense the number, like compared to your dimension, what do you sense the number of samples is? I think it's like n to the.
Yeah, I think where our barriers is more about the not being as that's the theoretical.
Yeah, but the dependence on this M is quite bad. I agree that, yeah.
I guess the answer I expected here is that somehow things like CNNs and transformers are very well suited somehow to approximate the distributions of images, at least.
Right.
Manifold. So I don't know how to make a more concrete statement. You didn't say that's big.
That might, yeah, that might also be a, yeah. So yeah, maybe their expressive power is much better compared to these feed-forward ReLU networks, which might also help. Yeah. Thanks for hosting me, and yeah,
Taking a look at your papers, but only briefly, so seeing you talk is always so much more insightful, you know, and can get to the point much quicker, so it's very interesting. Yeah, great.
yeah, it's been fun. Yeah.
I think we meet with the UA, with Chang.
Yes. Yes.
Oh,
Let me stop sharing.
actually, yeah. Oh,
Okay.
sorry, it came right at the end.
Yeah. And maybe. It's not great.
Yeah, is there? I haven't done it, but I would imagine they might be, yeah, quite related because flows, the true flow function is a linear combination of the scores, so they might be related. But one bottleneck is that for all this theory to hold, we can hammer in with Gersonov's theorem because we have, like in diffusions, you have a density, like things are diffusing on a space. But for flows, you're traveling with a ODE, which might not be that nice to handle.
Okay.
Hmm.